The next part of the lesson on the ImageStreamGang program is going to look at the structure and functionality of its overall design. And we're going to focus on integrating object-oriented and functional programming paradigms. That's really important. And this design we're going to examine really shows the way in which these two approaches work together more effectively than using either one of them in isolation. So here's the portion of the UML class diagram that shows the object-oriented decomposition of the ImageStreamGang app. So UML is the Unified Modeling Language. It's basically a way of ascribing semantics to diagrams. So you can have classes, you can have inheritance relations, you can have instantiation relations, you can have aggregation relations, and so on and so forth. All these classes, you can see there's well over a dozen classes here, apply various Java features, modern Java and object-oriented Java features and so on, to downloading and processing images. The basis of this whole case study is something called the StreamGang framework, and it's a reusable framework that allows streams to be initiated that process input from a list of elements. And we've seen this before in previous discussions of the SearchStreamGang case study. Unlike SearchStreamGang, which was designed to search the works of Shakespeare with various techniques, we have an ImageStreamGang subclass that extends the StreamGang framework. And this is, of course, there to customize the framework for downloading and processing images. We then have a whole bunch of different concurrency and parallelism mechanisms that are used to demonstrate these different modern Java features to run things concurrently and in parallel. So we have a sequential version, which is really just there as a baseline. We have a parallel streams version, which we're going to look at now. We have several different completable future variants we'll look at most likely next time we meet. And there'll also be a reactive streams implementation we'll look at later in the course as well. The ImageStream sequential class, as the name implies, downloads and filters images sequentially. That provides a baseline just to see how slow things can be if you only use one core. The parallel streams version, of course, will take advantage of multiple cores using the common fork join pool. And then we have a couple of different completable future implementations, one of which uses the common fork join pool, one of which uses a custom thread pool that we develop, and or rather we reuse something that's already defined in the Java executor framework, but it's not the common fork join pool. And that does the downloading and filtering asynchronously in parallel. There's also some other helper classes that are used. There's an image class that keeps track of images. There's a whole class hierarchy for doing filtering that uses the decorator pattern. So we can end up applying different kinds of image filters to process the images we've downloaded, transform them in some way or another, and then store them to persistent storage. And then there's also a set of classes that are used for the Android app user interface. And then there's also a console or command line version of this that doesn't require the use of Android as the GUI. So we'll spend less time focusing on the Android-centric stuff and focus primarily on the code that's independent of whether you use the Android platform or the Java platform. Now, if we run the ImageStreamGang app, but I won't actually run it here for the moment, but you're welcome to download it and run it because it's pretty cool. If you were to run it, one of the modes you run it, when you run it in the console version, it times how long the program takes to execute. And then it prints out the results based on the different strategies that you employ. And it, as always, because it uses the run timer framework, it'll print them out in sorted order from best performing to worst performing. So we have a couple of different types of images we process. The first one is using large images, so it's maybe a dozen or so large images. The second example is going to be about a dozen or so smaller images. And you can see in both cases, the completable futures implementation, which is where we're headed down the road here, is actually significantly faster than the parallel streams implementation, which itself is significantly faster than the sequential streams implementation. So the key point of this is to really help to reassure you a couple things. First, that parallel streams will typically run faster than sequential programs when you have large amounts of processing, which we do here because we have to download and do transforms and then store the images. So there's a lot of work going on. And secondly, that completable futures are often worth the effort because they typically run even faster. So even though they take more effort to program, the reward for the time invested is you get better performing code, which is a good thing. This particular set of results was achieved on a 6-core hyper-threaded Lenovo laptop with scads of memory and 2.6 gigahertz processors or processing cores. So your mileage may vary if you run it on a different processor with faster or slower cores and more or less memory and more or less cores and so on and so forth. But it does show you there's some important speedups we can get here. So that's the end of the overview of kind of the high-level walkthrough of the classes involved, and then giving you a sense of what the benefits are from using one approach versus another.